We have been studying Riemann integration for quite some time now. We defined the notion, we proved elementary properties of Riemann integral, and we also uncovered two quite large classes of Riemann integrable functions. But is every bounded function Riemann integrable? No. Here we have a function which is not Riemann integrable. So this section is just about this example. So let's see what it states. This result, this proposition. We have a function f whose domain is the closed bounded interval 0, 1 and it's real valued of course, and the rule for the function is this. Our x is of course coming from within this interval. If x belongs to the set of rational numbers, that is if x is rational, then the output is 1. But if x is irrational, then the output is 0. We have already encountered this function before. It's a very discontinuous function. This function obviously is bounded because its only values are 0 and 1. But this is not Riemann integrable. So let's prove this. Boundedness is obvious, so we will now prove that it's not Riemann integrable. Let P be any partition of our interval. Okay. Since this is a non-degenerate interval, which means that this is an interval which has positive length, the length is 1. So any partition will have at least one non-degenerate subinterval in it. Let J be any element in P. That means J itself is an interval which lies inside this. Now J may itself be non-degenerate or degenerate. We will see, okay. Suppose J is non-degenerate. That means J is neither the empty set nor is J a singleton set. In other words, J may be a closed interval, an open interval or a half open interval, but it has positive length. So it's non-degenerate. Then J contains a rational number as well as an irrational number. We know this fact. Okay, by now it's an elementary fact that any non-degenerate interval within the system of real numbers has at least one rational number and at least one irrational number. And that will tell us what? See, that tells us this. Now, if you look at the f values at the points x which are coming from J, at least one of those x values is 1 because J has at least one rational number. If you evaluate f at that rational number, you will get 1. Also, there is at least one irrational number in J. At that irrational number, if you evaluate f, you are going to get 0. Hence, we are going to get two things. The first is that the supremum of all the f values as x varies over j is equal to 1, because one of those f values is actually equal to 1, and that is the f value at that rational number. Similarly, the infimum of this is equal to 0, because we also have an irrational number and the f value at that irrational number is 0, because we have the 0 value inside the set itself. This is after all a set, no, it's the set of all f values as x varies over j, and this is the infimum of that set. Since we have the minimum possible value 0 within the set itself, the infimum is 0. Hence, this times the length of j. Let me put another set of brackets so that it's clear that we are multiplying this supremum and the length of j is equal to the length of j, and infimum of f of x as x varies over j times the length of j is 0, because this is 0. Note that the above equalities or equations, that means these equations, are also true if j is a singleton set A for some real number. In other words, if j is degenerate, we have taken j to be non-degenerate, but even if j is degenerate and degenerate of this type, where it's a singleton set, still these equations are true. Why? Well, if j is degenerate, then its length itself is 0 by definition. So this side is 0 and this side is 0. And in this case also, the left hand side is 0 because this is 0, and the right hand side is also 0. So these two things are true for all non-degenerate j as well as degenerate j of this type. We are not talking about the empty set, okay, degenerate of this type. Alright, so with these two things, now if we write the upper Riemann sum and lower Riemann sum of f for this partition P, what shall we get? Let's see. Thus, the upper Riemann sum of f for the partition P, let us first write what the upper Riemann sum is by definition. It's the summation of supremum of fx as x varies over j times the length of j. And how does the sum vary? I mean, what are the terms of the sum? It varies over all j coming from the partition P, but at the same time j is not the empty set. That means this. Okay, so j cannot be the empty set. J can still be a degenerate interval of this type. But because we have this, so this is equal to summation this. But that just gives us what? The length of the interval 0, 1 itself by a previous lemma. You recall this. If you take an interval of a partition of an interval and you add up the lengths of the subintervals in that partition, then that is equal to the length of the interval itself. And that length is what? Because our interval is 0, 1, that length is this itself. And in fact, if you want one more line, you can note this. This is the length of 0, 1, which is equal to 1. But how did we choose this partition? This partition was just any partition of our interval 0, 1. Regardless of what the partition actually is, this upper sum is equal to 1. Now, by a previous result, how do we link upper sums with upper Riemann integral? The upper Riemann integral turns out to be the greatest lower bound of the set of all upper sums. Because that set now has only one element, and that is 1, so the upper integral is 1. Hence, the upper integral of f is 1. Similarly, let's use this to calculate the lower Riemann sum and then the lower integral. In the book, these results have been referred, okay. By using which result you are saying that the upper Riemann integral is the GLB, greatest lower bound of the set of all upper sums. But that's understood. If you are following these things carefully, you know what result I am talking about, and anyway you can see the book. So I am not writing those things here again. Similarly, what about the lower Riemann sum? This is just like that, only in place of supremum you have infimum. X varies over j times the length of j, and j varies over all the non-empty elements of P. And we have already seen that in this case this is 0. So the lower Riemann sum is 0. Just like the upper integral is the greatest lower bound of the set of all upper sums, the lower Riemann integral is the least upper bound of all the lower Riemann sums, and all the lower Riemann sums are equal to 0. So the least upper bound is also 0. This implies the lower integral is equal to 0. So this is a function which, in spite of being bounded, is such that its upper and lower Riemann integrals do not match. So obviously, by definition, it's not Riemann integral. Since this is not equal to the upper integral, f is not Riemann integral. And that's the proof. After this result, there is one small remark with which the section itself ends. The remark draws our attention towards the rather artificial nature of this function. That is, we had to choose the function which is so bad that integrability is affected. It is artificial because it's really, the function is so wild. At every rational number, it's 1, and at every irrational number, it's 0. Most of the normal everyday function within the world of mathematics that we encounter are not like this. So most of the normal functions we encounter are in fact Riemann integrable if they are bounded. There are exceptions, of course, but the exceptions mostly are like this extreme, are of extreme nature. So Riemann integration, Riemann integrability is enough for most of our purposes, but still we need to improve this. We need to extend this theory to other integration theories. One of them is Liebig integration, Liebig integral, which we will discuss in the last chapter of this book. This book means in the second volume, in Analysis 2. In the very next section, however, we are going to see an extension of Riemann integration, and this is Riemann-Stieltjes integral. You have seen that we denote the Riemann integral of a function f over an interval I with this symbol. Riemann-Stieltjes integral is done again just like that of a function f over an interval I, but there is one more ingredient. There is a function alpha, and that alpha is itself just like f, a function from I into the set of real numbers, and alpha is monotonically increasing. We will see why we need this alpha and what the notion of this new integral is, and how its properties can be used to derive many more things about the Riemann integral itself. And one of those things is our familiar change of variables formula. You may recall that when we encounter things like this, say x sine x square dx, in school we were asked to integrate this thing. Right? What we used to do is we would make a kind of substitution, or we change the variable from x to t. What do you then do? You write this: 2x dx equal to dt, where differentials appear. We haven't actually used differentials so far anywhere in this book. But for some reason in school, without understanding really much about what is going on, we just do it. And then x dx turns out to be 1 over 2 dt. So when you change the variable from x to t, in place of x dx, sine x square of course becomes sine t, and here you write dt divided by 2. And then you integrate sine t, get minus cos t plus the arbitrary constant, all those things. Why does it even work? And what does it actually mean? We are going to prove these things, and we will also see why we can change variables like this with the help of Riemann-Stieltjes integral. and the next section is going to be a bit longer than the other sections. Definitely not this short. And this is an exceptional section. No, it just tells us one example. So these are the things we are next going to see in analysis. So that's just it for tonight. Tomorrow also we have our upload, and what shall we do tomorrow? Because we have already done trigonometry last week, no? So tomorrow let's again go back to number theory. So see you tomorrow with number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.